I was looking up at the night sky the other night, and it's just so deceptively calm.
Oh,
You
absolutely.
see these little pinpricks of light, and they feel eternal, like they've
No.
always been there, always will be.
But if you actually, look under the hood of the universe, it's anything but calm.
It's a war, a constant high-stakes war,
It really is. Every single one of those stars is in a billion-year wrestling match with itself.
a balancing act.
A balancing act between two massive opposing forces. And the scary part is that the stalemate can't last. Eventually, one side wins, and the star dies.
And how it dies, whether it's a quiet little whimper or a bang that outshines an entire galaxy, that all comes down to its weight.
It's all about the mass it was born with.
So today we're doing a deep dive into stellar endgames. We're going to track the life cycle of stars from their bloated red giant phase to the dense graveyards of white dwarfs.
All the way to the cataclysm of a supernova and, of course, the ultimate victory of gravity, black holes.
And we have a pretty serious stack of sources for this. We're pulling from Stephen Hawking's A Brief History of Time and the Universe in a nutshell.
And then weaving in some Carl Sagan from Cosmos, Neil deGrasse Tyson's Astrophysics for People in a Hurry.
And even a little Brian Greene from The Elegant Universe. A literal all-star team.
Couldn't resist.
So let's start with that wrestling match, that central conflict. Hawking uses an analogy for this, doesn't he? A balloon.
He does, and it's a great one. Think of a normal balloon. The rubber is always trying to contract, to shrink.
Okay.
In a star, that rubber is gravity. Just this relentless force, always trying to crush everything down to a single point.
But a balloon doesn't collapse because there's air pressure inside pushing out.
Right. And in a star, that air pressure is the incredible energy from nuclear fusion. Deep in the core, you have hydrogen atoms being smashed together to make helium.
And that releases a ton of energy. Heat.
An immense amount. So you have gravity pulling in, fusion pushing out. As long as they're balanced, the star is stable.
Yeah. But here's the catch, isn't it? Gravity is free. It's always there.
Always.
But that outward pressure that costs fuel, you have to keep burning hydrogen.
And that's where the countdown begins. Because every fuel tank, eventually runs dry.
Which leads to this paradox that Hawking points out. You'd think a really massive star, say 20 times the sun's mass, would live longer.
Right. It's got a much bigger fuel tank, way more hydrogen.
It should go for eons.
But it's the complete opposite. Massive stars are the rock stars of the cosmos. They live fast and die young.
Because all that extra mass, all that extra gravity, means they have to burn their fuel furiously just to stay alive.
Exactly. It's like comparing a little hybrid car to a Saturn V rocket. The rocket has more fuel, sure, but it burns through it in minutes.
Our sun is that sensible hybrid. It's got about 10 billion years worth of fuel in the tank.
But a massive star cranks the thermostat so high that it might burn through its entire supply in just a few million years.
So walk us through it. The hydrogen starts to run out. The engine sputters.
The outward pressure drops. And gravity, which has been waiting patiently for billions of years, finally makes its move.
It starts crushing the core.
It does. But here's the twist. That crushing action creates an enormous amount of heat. The core compresses. It gets hotter and hotter until, bang! It gets hot enough to start fusing the ash from the last reaction.
The helium.
The helium. Sagan has that beautiful line, the ash becomes fuel.
So the star gets a second life.
A second, very different life. This new helium-burning engine is much, much hotter, and it causes the outer layers of the star to just swell up.
It's not dying yet, it's just transforming.
It's becoming a red giant.
And we should pause here because this isn't some abstract thing. This is a direct prophecy for our solar system.
It is. This is the fate of our sun. Sagan maps it out. In about 5, maybe 6 billion years, the sun runs out of hydrogen.
It starts burning helium.
And it will bloat up, becoming ruddy and huge. It'll expand right past the orbit of Mercury.
Then Venus? What about Earth?
It's not looking good for property values. The Earth will almost certainly be swallowed.
Wow.
The entire inner solar system will basically be inside the sun's atmosphere.
That's a terrifying thought. The sun going from this little dot in the sky to filling the whole sky, to being the sky.
It's visceral. But even that helium runs out eventually. And for a star like our sun, a low to medium mass star, that's the end of the line. It can't get hot enough to fuse the next element, carbon.
So the red giant phase ends. The star just puffs off those outer layers.
It sheds them, yeah. And that creates these incredibly beautiful planetary nebulae you see in photos. The leftovers.
The ghost of the sun. And what's left behind in the middle is the core, The first tombstone in our stellar graveyard.
A white dwarf.
And dwarf is really the right word. You're taking something with the mass of the sun,
Which has the volume of 1,000,000 Earths.
and you're squeezing it into a ball the size of the Earth.
The density is it's off the charts. We're talking hundreds of tons per cubic inch.
So here's the physics question. What's holding it up? There's no fusion anymore. The heat's gone. Why doesn't gravity just finish the job and crush it completely?
This is where we get into the quantum weirdness. Brian Greene talks about this. It's called the Pauli exclusion principle.
Okay.
In really simple terms, electrons are, well, they're antisocial. They hate being in the same state in the same place.
So gravity is trying to shove them all into the same tiny room.
And they're pushing back. They're basically saying, nope, we can't be squeezed any closer together.
So it's not heat holding the star up anymore. It's electron claustrophobia.
Chuckles. That's a perfect way to put it. It's called electron degeneracy pressure. And for a long time, physicists thought this force was invincible. A white dwarf would just sit there and cool off forever.
But then a young guy named Subramanian Chandrasekhar comes along and figures out that even electrons have a breaking point.
This is one of the best stories in Hawking's book. It's 1928. Chandrasekhar is just 19 years old on a ship from India to England.
No computers, just a notebook.
Just a notebook and the stars above the ocean. And he starts doing the math on this electron pressure.
And he finds a limit.
He finds a hard limit. He realizes that if the star's core is massive enough, about 1.4 times the mass of our sun, the gravity is so intense.
It's so intense
that the electrons would have to move faster than the speed of light to resist it.
which, according to Einstein, is a cosmic no-no.
It's illegal. The laws of relativity just forbid it, so the whole structure has to fail.
So any star above this limit, the Chandrasekhar limit, can't become a white dwarf. It has to collapse even further.
Exactly. And at the time, this was a crazy idea. The top astronomer in the world, Sir Arthur Eddington, basically laughed him off the stage.
He just couldn't accept that a star could keep collapsing forever.
He couldn't. It took decades for Chandrasekhar to be proven right. But he was. If you're below the limit, you get a quiet retirement as a white dwarf. If you're above it, well, you get a spectacular death.
Let's talk about those heavyweights. They crush right past the white dwarf stage. The core gets so hot and dense, it just keeps fusing heavier elements.
It just keeps going up the periodic table. It fuses carbon into oxygen, oxygen into neon, neon into silicon.
It builds up in layers like an onion.
Exactly. But then it hits a brick wall. And that wall is made of iron.
Neil deGrasse Tyson calls iron the stellar killer. What's so special about iron?
It all comes down to energy. For every element lighter than iron, when you fuse it, you get energy out. It's a profitable reaction. It gives you the heat you need to fight gravity.
But iron is different.
Iron is different. It has the most stable, tightly bound nucleus of any element. To fuse it into something heavier, you don't get energy out.
You have to put energy in.
Right, it's an energy vampire. Instead of producing heat, it starts sucking heat out of the core.
So the star's power source, the thing that's held it up for millions of years, just turns off.
In a fraction of a second, it's gone. The outward pressure just vanishes.
And we have to stress the speed here. This isn't a slow leak.
No, Tyson says the collapse happens at about a quarter of the speed of light. The core, which is the size of Earth, shrinks down to the size of a city in less than a second.
Imagine the entire planet Earth collapsing to the size of Manhattan.
In the blink of an eye, the rest of the star, all those outer layers, come screaming inward, hits that new super dense neutron core, and bounces.
And the bounce is the supernova.
The bounce is the supernova, a shockwave that just obliterates the star. For a couple of weeks, that one explosion can outshine its entire galaxy.
And we've seen these happen. This isn't just theory.
Oh, absolutely. Chinese astronomers in 1054 recorded a guest star that was so bright you could see it during the day. That's the Crab Nebula we see today.
Now, Carl Sagan makes this profound point. We see this as destruction, as death. But really, it's the most creative event in the universe.
It's the whole we are star stuff idea. The Big Bang only made hydrogen and helium. That's it.
Pretty boring.
Very boring. All the elements of life, the carbon, the nitrogen, the oxygen, the iron in your blood, all of that was cooked inside stars.
And the really heavy stuff, the gold on your finger, the uranium.
That's only made in the supernova explosion itself. The incredible pressure of that shockwave forges those elements and then blasts them out across the galaxy.
So we're literally made of the nuclear waste of long-dead stars.
Recycled stellar debris, sitting here talking about it.
It's just humbling. So, okay, the smoke clears, the outer layers are gone. What's left behind? that city-sized ball of neutrons.
The neutron star. This is the fate for a core that's too heavy to be a white dwarf, but not quite heavy enough to become a black hole.
Give us a sense of the density. A white dwarf was hundreds of tons per cubic inch. Where are we now?
We're in a place that breaks the imagination. The pressure is so great that electrons have been physically forced into protons to become neutrons. All the empty space is gone.
So single teaspoon.
A single teaspoon of neutron star material would weigh as much as Mount Everest.
If you tried to put that spoon on a table, it would just...
It would drop through the table, through the floor, through the crust of the Earth. Sagan figures it would just oscillate back and forth through the center of the planet like a hot knife through butter.
And they spin incredibly fast.
But unbelievably fast. Because of conservation of angular momentum, the original star might have spun once a month. Squeeze it down to the size of a city, and it might spin hundreds of times a second.
And some of them have these magnetic fields that shoot out beams of energy.
And if those beams happen to sweep past Earth, we see a pulse. Tick, tick, tick. We call them pulsars. They are the most accurate clocks in the known universe.
But even a neutron star has its limits. There's one final weight class. If that leftover core is more than, say, 3 times the mass of the sun,
gravity wins. It wins completely. There is no known force in the universe that can stop the final collapse.
not electron pressure, not neutron pressure, nothing.
Nothing. The star shrinks past the size of a city, past the size of a walnut, all the way down to a point of zero size and infinite density.
A singularity.
A black hole. A place where gravity is so strong that not even light can escape.
I want to get into what that would be like. Hawking has this gruesome description of falling in. Spaghettification.
It sounds funny, but it's a real term for a tidal force. As you fall feet first, your feet are just a little bit closer to the singularity than your head is.
On Earth, that difference is nothing.
It's meaningless. But near a black hole, the force of gravity increases so dramatically over that short distance that the pull on your feet is immensely stronger than the pull on your head.
It stretches you.
It stretches you into a long, thin noodle of atoms before you even get to the center.
And the weirdest part is what someone watching from a distance would see.
That's maybe the weirdest part of all. If I'm watching you fall in, I never see you cross the boundary, the event horizon.
Why not?
Because the light from your body has to fight so hard against gravity to reach me that it loses energy. It gets redder and dimmer. Your movements slow down until you just seem to freeze on the edge and fade away forever.
But from my perspective, I've already crossed over and been turned into spaghetti.
It completely breaks our everyday intuition about time and space.
Now, for a long time, these were just, ghosts in the math. Einstein didn't really like them. But we know they're real now. And there's a great story about a bet Stephen Hawking made.
Chuckles. The Cygnus X1 bet. Yes. So astronomers found this X-ray source, Cygnus X1. They saw a normal star orbiting, something invisible.
And that invisible something was ripping gas off the star.
Right. And the math showed it was too massive to be a neutron star. It had to be a black hole. But Hawking, who built his career on black holes, bet his friend Kip Thorne that it was not a black hole.
He bet against his own life's work. Why?
He called it an insurance policy. He figured if it turned out black holes weren't real, he'd have wasted years of his life, but at least he'd win the bet.
What were the stakes? This is the best part.
It was very 1970s. If Hawking won, Thorne owed him a 4-year subscription to a satirical magazine. If Thorne won, meaning black holes were real,
Hawking had to buy him a subscription to Penthouse.
a 1-year subscription to Penthouse magazine.
Yes. The greatest minds in physics betting pornography on the fundamental nature of the cosmos. I love it.
And Hawking did pay up. By 1990, the evidence was overwhelming. We now know they're real. There are supermassive ones at the center of basically every galaxy.
So we've come full circle. From gas cloud to fusion engine to these exotic corpses, white dwarfs, neutron stars, black holes. But let's end by going back to that idea of recycling.
It's so important. The death of a star is never just an end. That supernova shockwave doesn't just spread out elements.
It acts like a trigger.
It slams into other nearby clouds of gas and dust and compresses them. That compression is what kickstarts gravity's pull to form the next generation of stars.
The death rattle of one star is the birth cry of the next.
It is a continuous cosmic cycle of creation. Without those violent deaths, there'd be no heavy elements, no planets, no us.
And if we zoom all the way out to the very end of everything, Hawking touches on this.
He does. The old idea was a big crunch, where gravity eventually pulls the whole universe back in. But the data now points to a heat death.
The long, cold whimper.
The universe just keeps expanding and cooling. Eventually, all the stars burn out. The black holes evaporate over trillions of years, and you're left with a cold, dark, empty void.
Well, on that cheerful note,
Yeah,
but I think Carl Sagan actually has the best final image.
yeah.
He brings it back to Alice in Wonderland.
The Cheshire Cat.
He says a black hole is like the Cheshire Cat. The cat itself vanishes. The matter of the star, the light, it's all gone from our universe.
But something is left behind.
The grin.
The grin, the gravity, the deep curve in space-time that the star created. Even after the star itself is gone, its influence, its grin, is still there, holding the galaxy together.
A reminder that nothing is ever truly lost. The energy, the gravity, it all endures.
And it's because of those vanishing cats that we have the gold in our phones and the iron in our blood.
We are star stuff, contemplating the stars. Seems like a good place to leave it.
Sure.
Thanks for taking this deep dive with us.
My pleasure.
We'll see you on the next one. Keep looking up.